Hello. In this video, we begin our study of infinite sequences and series. So as we embark upon this journey, I wanted to motivate some of the things that we're going to get into in this study. And so this short little video is going to introduce you to one example. We're going to explore the graph of the sine function, and I'll try to tease some of the things that we're going to build to over the course of the remainder of the semester. And along the way, I'll talk briefly about how this unit fits into the broader theme of calculus at large. So on the first slide here, I'm recommending that you plot the sine function on the Desmos app, and on the same set of axes, start to plot these polynomial functions that I've listed down below. So yeah, in case you hadn't noticed that, these are all polynomial functions. You'll notice the first one is a linear function. The second one is a cubic function. The next one's a fifth power, or you could call it a quintic function. And you may also notice that they're all kind of tied together in the sense that, for example, in function f sub 2 down here, notice that the first two terms are exactly the same as what f1 itself was. So for instance, f sub 2 is the exact same thing as f sub 1 of x, plus that third term, the fifth power, 1 over 120 x to the fifth. And continuing that pattern, f sub 3, that function, is the exact same as the f sub 2 function. These first three terms are the same as f2 itself, minus that last term, the 1 over 5,760 x to the 7th. So I'm just hoping that you pick up on that pattern in these functions here, that you notice that they're all polynomials. They all involve just nice whole number powers of x being added and subtracted. Why it's only seemingly the odd powers of x, the third, the fifth, the seventh, and why it's these particular seemingly random numbers, the 5,760, the 120, don't worry about that for now. We're going to get into that over the next several weeks. Just for now, I want you to notice that there's some pattern in here. These aren't four random functions that I'm making you plot. So why don't you take a minute, plot those for yourself, see what you notice, any interesting observations you can make, any patterns that appear, anything that you could describe to somebody else looking along with you. And along with that, what do you wonder? Anything that you notice that makes you ask a question, or there's anything that you'd want to explore more, or any questions that make you go, why is that? When you're ready, you can click on or type in that URL for Desmos at the bottom there, and you'll see what I'm about to pull up in a minute after you unpause. So here's that Desmos graph that you'll see if you click on that URL, something like this. I've graphed the sine function, that's the red curve, the wave that you see. Don't worry about the magic sauce there in the green part that you see in the second thing there. That's just me typing to get a list of those functions, the four ones that I gave you on the slide. This is my condensed way of putting that into a pattern. And over the course of the next couple weeks, we'll unpack what this notation means and why it's this particular pattern. But for now, what you can do is you see this slider bar where it says n equals 0. That is plotting right now f sub 0. The green line that you see, it comes from the second second item in the list on the left here, the one with the blue box around it. And when n is 0, it's plotting f sub 0. In fact, that's exactly the function f sub 0 that I gave you back here. That's the straight line y equals x, so you can see that. The next function, f sub 1, was going to be a cubic function. So if I go back to Desmos and I scroll my n slider bar over to the right a little bit, or you can just go in here and type 1 for n if you'd like, notice that I now am plotting a cubic. And according to this thing that I've typed up here, it's following the exact pattern to graph for you f sub 1 that I gave you on the slide. And so then you can scroll this n slider bar to see those happening. Or you can uncheck that, and you can just plot the first couple that I asked you on the slide there, so you can see them all at once if you'd prefer to do that. So what do you notice as I make n bigger? As I start to graph more and more of these functions, I add more terms, because we notice the pattern where each function was the one before it plus or minus something extra. So right now, this is a straight line, obviously not equal to the sine function. But around 0, they're pretty close. They agree at 0, 0. And if I zoom in a lot, you almost can't tell that they're different. I can see the sine wave is curving a little bit in the top right quadrant and the bottom left quadrant, but if I zoom in even further, those differences start to dissipate away and you can't tell that they're different. But if I zoom back out, it becomes glaringly obvious that my straight line is not a great estimate for the sine function elsewhere away from 0. So let's bump that up and look at f sub 1. Well, that improves things quite a bit. If I zoom in around x equals 0, I don't have to zoom in nearly as much to see that it's a really good estimate. Notice the width here is from -1 over to 1. Even on that domain, I almost can't tell that these are different curves. And only when I start to zoom out a bit do I notice that the curve that I'm graphing, the green one, starts to deviate from the sine wave. If I zoom out even further, I can see, well, it's obviously going to be a bad estimate further away from 0 because the sine curve just keeps oscillating between -1 and 1, but the cubic function is going to grow to positive infinity and negative infinity. But look what happens if I add another term and I bump it up to n equals 2. Wow, this is really good between -2 and +2 for x. And only if I zoom out even farther do you start to see that they're different. And as I keep adding terms, I'm going to zoom out quite a bit so you can see this effect. There's the sine wave traveling left and right, and there's my, right now, 5th power quintic function. And as I add terms to it and I make n bigger, look at that. It's just kind of laying more pieces of the curve on top of the sine wave. It's becoming a better and better estimate. So here I now have essentially f sub 20, and I'm graphing that. If I zoom in, wow, if I didn't tell you what I was doing, you wouldn't even know that there are two curves being plotted here. You would just see a green wave, and it would look exactly like the sine wave. And only if you zoomed out really far would you see that there are two graphs going on. So let's go back down to something like f sub 2. There's something even more happening here. I said that this is a pretty good estimate for some values of x around 0. So not only as I zoom out on the big picture, as I add more terms, does this graph become a better approximation of the sine function at large on the wider domain. Not only that, but as I add more terms, the estimate that you see around 0 is also improving. So let me show you stuff that I have down here in the bottom left to convince you of that. The blue dot on the curve there, you can move around for yourself. So let me back up to the line. When you move, click and drag that blue dot, it stays on the sine curve. So it's plotting a particular point, and you can even go down here and change A this way, or you can just go in and straight up type a number for A if you wanted to. I'm just going to type, let's do, well, you know what, let's do pi over 2. Because we should know that the sine of pi over 2 is exactly 1. So that's what you see in this box right here. F of A, that's the sine value of A. And you can see that it's exactly 1. There's that point over there, pi over 2, 1. And now what I have down here when it says F sub n of A, it tells you the green curve's prediction of what happens when I plug in the same A. So when I plug in pi over 2, the output of the straight line y equals x is going to output pi over 2. And so that's this point up here around 1.57 or so. And there I've added some labels for the 2 points we're talking about. The blue point on the red curve there is, you can think of that as a value we're trying to approximate. I picked pi over 2 just because we happen to know exactly that the output should be 1. But notice how the green curve is not particularly accurate. It's outputting pi over 2 when it's supposed to, quote unquote, be outputting 1. And so you can see that down here on the left. The f of A is the y-coordinate of the point on the sine curve. The f sub n of A is the y-coordinate of the point on the green curve. And this calculation I have down here is a percent error. It says essentially that right now, our estimate with the green curve is 57% off. We're supposed to be getting an output of 1. We're getting an output of 1.57. And so you can see where that 57% is coming from. We're 0.57 off out of a total value that's supposed to be 1. And so notice what happens visually as I add more terms to the function, as I move n bigger. All of a sudden that point jumps a lot closer. Now we're outputting 0.925, we're talking about a 7.5% error, much closer. If I add another term, all of a sudden that's pretty close, 1.005. That's a 0.45% error. Remember, that's not 45%, that's 0.45, under 1%. That's almost exactly the same. And as I keep adding points, eventually, it's so close that Desmos just displays 1 there. It's not exactly 1, it's 0.9998. It's just rounded up. And I can see it's a 0.01%. And as I keep adding more terms, that estimate becomes very, very, very good, almost practically the same. You can see now here my error is 0.00014 zeros percent. So that's really close. Let me jump back to the line. And let's move the blue point over. Oops, I have to change A down here. Let's add a slider for A. And so let's make it something like that. Notice how my line is way off now. It's supposed to be outputting 0.598 and I'm outputting 2.5. That's a whopping 300+% error. And as I add more terms, and remember globally zooming out, as I add more terms, this is making more of the curve lay down on top of the sine function. Notice how that even by adding the second term, I'm a little bit closer, and now I have a, well, still 117% error, which is terrible, but much better than the first estimate we had. As I add another term, oh wow, much closer, about an 18% error. And then I add another term, and they're practically the same thing, and now I'm down to 1% error. And as I keep adding, so I lost that value, as I keep adding terms, I would see that estimate become practically 0 error. And so if I move that blue dot like way over here to the right, that's way off. Even with this high number of terms that I have so far, I can see a 13,000% error. But if I keep adding enough terms, eventually those points are pretty much on top of each other and I have an under 1% error. So there's something going on here where as I add more terms to this function, as I plot f0, f1, f2, f3, and so on, and I keep adding more, I get better estimates of the numbers near 0, and I get better estimates farther away from 0. It just takes longer to get there. And so there's something going on here where essentially if I were able to add infinitely many terms to this function, I literally would get the sine function. In a very real sense that we're going to explore over the next few weeks, the sine function that we have come to know and love, or at least like, I hope, that sine function really does literally equal the limit of this expression. If I were to add more and more, if I could add infinitely many terms to this summation, to this function here, this polynomial, then I would get exactly the sine function. So it turns out these are building up the Taylor series of the sine function. So I'll leave this as a little teaser if you want to do some quick Googling around or looking ahead in our notes or the textbook. That's what this is a preview of. And this is where we're building towards over the next couple of weeks that we have left in the semester. And everything we're doing in the meantime, try to have this motivation, this example, in mind as we're going through it. We're going to have to talk about what I mean by a sequence. We're going to have to talk about what I mean by a series. We're going to have to explore where these functions are coming from. What's the pattern in those seemingly random numbers that are in the denominators there? Why those? And why are they adding up to the sine function? Could I do this for other functions like e to the x or natural log or the square root function? We're going to answer all of these questions as we move on. So really quickly now, I'm just going to mention that this also fits into the major themes of calculus in a couple of ways. The big one, I think, is we're dealing with infinity. That's a big theme. You talked about limits in Calculus 1 and how, for example, like the limit as x goes to infinity of 1 over x, how that equals 0, in the sense that the 1 over x function approaches. It gets closer and closer to outputting 0 as I make my input x bigger and bigger and bigger. It never outputs exactly 0. I can't solve for x in this equation to make it equal to 0, but I can make it arbitrarily close to 0. I can make 1 over x as close to 0 as I could possibly want. That's a way you dealt with infinity in Calc 1. We dealt with it in Calc 2 by talking about improper integrals and infinitely wide domains of integration, and we talked about those integrals converging or diverging. We're going to use those terms a lot in this study of sequences and series. Converging meaning approaching a specific number, and diverging meaning doing something else, not approaching a specific number. We're also going to be talking a lot about limits. That naturally ties in with infinity and converging, approaching something. But I just want to remind you that a definite integral is also a limit. Remember that we would take the graph of a function, we would take some region like this and split it up into a bunch of small rectangles, add up their areas, and say that's a good estimate, an approximation for the area under the curve, and then that adding together is stitching those small pieces back together. And then if we took a limit as the number of rectangles grows to infinity, that's how we would recover the exact area under the curve. That's what an integral is. So these are ideas that we've touched upon before in calculus, in Calc 1 and Calc 2. One kind of new one that will pop up is what I was trying to motivate with that sine graph we were just looking at, the idea of numerically approximating. Saying that there's an answer we're trying to get and recognizing that we can't get it exactly, but finding estimates, numerical values that are approaching it, that are getting as close as we could possibly want. So one thing that I've mentioned in class before is that, for example, the antiderivative of e to the x squared, quote unquote, doesn't exist in the sense that we can't write it down nicely using functions we know and love like polynomials and square roots and sines and exponentials. There's no way to write down a nice expression that equals a function whose derivative is perfectly e to the x squared. So this is an integral that we just haven't tackled because we can't. Now, using these infinite sequences and series, we'll actually be able to come up with an expression that, in the sense that I was saying earlier, if I could add up all of the terms of this summation and add all of the terms to that function, I would get it equal to the sine function. Well, that's an arguably somewhat nice way to write down a function, and that's pretty much how we're going to tackle this problem. We're going to come up with a antiderivative of e to the x squared, but it's going to be not quite nice in the sense that it's an infinite sum. It's not just a finite number of pieces added together. And then we'll use that to actually address this definite integral here. We'll find the area under the e to the x squared curve, which looks something very steep like this. We'll be able to answer what is the area under this graph of e to the x squared from 0 to 1. And here's the magical thing. Even though we don't have a way of writing down exactly what that number is, other than saying it's the answer to this problem, we'll be able to estimate that area and declare with 100% certainty how close it is. We'll be able to say, well, here's a number and it's at most 10% off. Or here's another number and it's at most 2% off. Even though we don't know exactly what the correct answer is supposed to be, we can get within a desired threshold of that number. And I find that absolutely magical, and that's something we're going to build to over the course of our study of sequences and series here.